close your eyes and picture the darkness between galaxies. Not the dark of a closed room, but a deeper dark, one that stretches for millions of light years without a single star to interrupt it. Out here, the silence is total. No sound has ever traveled through this emptiness, because sound needs something to move through, and there is almost nothing here at all now. Let your mind drift back toward home, back through the space between galaxy clusters, back past great rivers of stars bound together by gravity, back toward one ordinary spiral galaxy holding 400 billion suns. Somewhere inside that galaxy, near one unremarkable star, a small blue planet turns slowly in the dark. Everything you have ever known has happened there. Every sunrise, every breath, every quiet night like this. It is strange to think that this small, warm place should exist at all, not because life is fragile, though it is, but because the universe itself seems to have been built with a precision that is hard to explain. The strength of gravity, the pull that holds galaxies together, sits at a very particular value. The force that binds atomic nuclei sits at another. The rate at which space itself is expanding sits at a third. Nudge any of these numbers even slightly, and by most calculations, stars would never form, atoms would never bond, and nothing like a night sky or a listener drifting off beneath it would ever come to be. Physicists call these values the constants of nature. They are numbers that seem to be fixed throughout the universe, numbers that show up again and again in the equations that describe how matter and energy behave. And what troubles some physicists, in the gentlest and most fascinating way, is how narrow the range of workable values seems to be. It is a puzzle sometimes called fine-tuning, and it sits at the center of one of the oldest open questions in science. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like, one waiting each evening, subscribe and let it find you. Think of it like a knife balanced on its edge. Tip it even a little one way and it falls. Tip it the other way and it falls just as easily. Only one narrow position lets it stand at all. Some researchers look at the constants of physics and see something similar, a set of numbers standing upright on an edge far narrower than chance alone would predict. But here, the agreement ends and the wondering begins. One idea is that this balance points to some deeper law we have not yet found, a hidden structure that makes these values the only ones mathematically possible. Under this view, the universe is not lucky. It is simply the one way things could have worked out, and we have not yet found the equation that shows why. Another idea reaches further outward. Perhaps our universe is only one among countless others, each with its own random set of constants, most of them barren and dark, incapable of forming atoms or stars or anything at all. Under this view, we do not live in a universe fine-tuned for us. We live in one of the rare universes that happen to work, because only in a working universe could anyone exist to notice. And a third possibility asks us to be careful about how surprised we allow ourselves to be. If life can only arise in a universe suited to life, then of course we would find ourselves in such a universe. Observing fine-tuning may say less about the universe's design and more about the limits of who is doing the observing. This idea, sometimes called the Anthropic principle, is itself the subject of quiet, ongoing debate among physicists and philosophers alike. None of these ideas has been confirmed. None can yet be tested in a way that settles the matter. We simply do not know tonight whether the universe's suitability for stars and atoms and quiet nights like this one is a sign of hidden law, a matter of cosmic luck among many universes, or a kind of question we are not built to answer from the inside. For now, it is enough to notice the knife's edge and to feel, in the most peaceful way, how strange it is that we are here to notice it at all. In the sections ahead, we will look closer at the numbers themselves, at the forces that hold nuclei together, at the strange near emptiness of space, and at the scientists who first began asking why the universe seems built the way it is. There is no rush. The dark between the stars has waited billions of years. It can wait a little longer while we rest and wonder together. Let's rest inside the atom for a while. Deep in the center of every atom sits a tiny core called the nucleus. It holds protons and neutrons pressed close together, closer than anything else in nature. Something has to hold them there, because protons carry a positive charge, and charges that match tend to push each other away. That something is called the strong nuclear force. It is one of the 4 basic forces that shape everything in the universe, alongside gravity, electromagnetism, and the weak force. The strong force is, true to its name, the strongest of the 4, but it only works across a very short range, smaller than the width of a nucleus itself. Picture 2 marbles pressed together, each one buzzing with a charge that wants to fling the other away. Now picture an invisible hand gripping them so tightly that the push cannot win. That grip is the strong force. It has to be strong enough to beat the repulsion between protons, but not so strong that it crushes everything into a single dense clump. Here is where the puzzle begins. The strength of this force is set by a number physicists call a coupling constant. It is just a number, fixed since the earliest moments of the universe, with no obvious reason for the value it holds. And that number turns out to sit inside a strangely narrow comfort zone. If the strong force were only a few % weaker, atomic nuclei would not hold together at all. Hydrogen might be the only element the universe could ever make. No carbon, no oxygen, no chemistry complex enough to build a star's core into something more, let alone a planet, or skin, or breath. If the strong force were a few % stronger, the opposite problem appears. Protons would bind so easily that hydrogen itself would become rare. Some researchers who study this question believe that stars might struggle to shine the way they do, because the slow fusion that powers a sun depends on hydrogen sticking around, resisting fusion, just enough to burn slowly over billions of years, rather than all at once. This narrow window is not a matter of guesswork or rough estimate. It comes from decades of nuclear physics, testing how particles behave under different conditions, and running the numbers forward to see what kind of universe would result. The window is real. What remains genuinely open is why the value landed inside it at all. One idea is that the number simply is what it is, a brute fact with no deeper cause. The same way some people accept that a coin lands heads without asking why the universe chose heads. Under this view, the fine placement is not mysterious. It is only the value we happen to observe, and every other value would be equally arbitrary. A different idea reaches further. Some physicists wonder whether this number, and others like it, might vary from one region of space to another, or from one universe to another, if such other universes exist at all. Under that kind of framework, most versions of a universe would have nuclei that never form, or form too easily, and never develop anything as intricate as chemistry. Only the rare versions with a well-balanced strong force would ever produce anyone able to notice the balance. This is one small piece of a much larger question the episode will keep returning to, about whether we are simply observing the only kind of universe capable of holding an observer. Neither idea has been confirmed. There is no experiment yet that can look outside our own universe to check, and even within our universe, physicists still do not have a complete theory that predicts why the strong force takes the exact value it does, rather than some other value nearby. What we do know is smaller and more grounded, but no less remarkable. Every carbon atom in a redwood tree, every oxygen molecule drawn into a sleeping lung tonight, exists because of a force calibrated with a precision that still has no accepted explanation. The nucleus at the center of every atom in your body is a quiet monument to a number nobody fully understands. It is worth sitting with that for a moment, without needing to solve it. The atoms holding you together tonight rely on a force whose strength seems to have been set with unusual care. Whether that care reflects a hidden law of nature, one outcome among countless universes, or simply the way things happen to be, remains an open question drifting quietly beneath the world of ordinary things. For now, the nucleus holds, the atoms stay whole, and the reason why still waits somewhere in the dark, unanswered. Let's turn now to gravity, the softest voice in the room of physics. Of all the forces that shape our universe, gravity is by far the weakest. It is so weak that a small magnet can lift a paperclip off a table, defeating the gravitational pull of an entire planet. And yet, gravity is the force that built everything large. It gathered gas into stars. It pulled stars into galaxies. It shaped the slow, patient architecture of the cosmos we see tonight. Physicists measure gravity's strength with a number called the gravitational constant, compared to the strong nuclear force we spoke of a moment ago. Gravity is weaker by a factor almost too large to picture, something like 10 to the 36th power. That is a 1 followed by 36 zeros. It is a strange kind of whisper, this force, and yet the whisper is precisely tuned. If gravity were only a little bit stronger, stars would burn through their fuel in a few million years instead of billions. Life, which seems to need long stretches of calm starlight, might never have had time to begin. If gravity were a little bit weaker, the opposite problem appears. Gas clouds would struggle to pull themselves together at all. Stars might never ignite, galaxies might never form. The universe might have stayed a thin, quiet mist of scattered atoms, drifting forever in the dark without ever gathering into anything resembling a sum. This narrow window is part of what researchers call fine-tuning. The idea that many of the numbers in physics sit inside a strangely narrow range that allows complexity to exist at all. Gravity's weakness sits at the center of this puzzle. Some physicists find it suspicious that a force so faint could still be exactly strong enough to shape galaxies without collapsing them too quickly. Others caution that exactly right may be a trick of perspective, since a universe with different gravity might simply produce a different kind of structure, one we have never imagined and cannot easily picture. Gravity's story becomes even stranger when we ask how it was born. In the earliest fractions of a second after the Big Bang, many physicists believe all the forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, might have existed as a single unified force. As the infant universe cooled, that unity broke apart, and gravity separated out first, becoming its own distinct presence. Why gravity split off with such a small strength compared to the others remains an open question. No one has observed this separation directly. It exists, mostly in the mathematics of theoretical physics, in models that try to describe conditions far beyond anything we can test in a laboratory. One idea, drawn from string theory, suggests gravity might seem weak, simply because it is spread thin. Some versions of string theory propose that space has extra dimensions, hidden and curled up far smaller than an atom. If gravity alone can leak into these extra dimensions, while the other forces cannot, that could explain why we feel it so faintly here in our three familiar dimensions of space. It is an elegant idea, but it remains unproven, resting on mathematics that has not yet been confirmed by direct observation. A competing view holds that gravity's weakness needs no exotic explanation at all. Perhaps it is simply a fixed feature of this universe, a number set at the very beginning for reasons we may never uncover. On this view, asking why gravity is weak is a little like asking why a circle is round. It might just be a basic property, not a puzzle waiting for a hidden mechanism to explain it. There is also the deeper anthropic question. If gravity's whisper is exactly what allows galaxies, stars, and planets to form slowly enough for life to arise, is that a coincidence worth wondering about? Or is it simply the only kind of universe where anyone would exist to notice? A universe with the wrong gravity might not be empty in some tragic sense. It might simply be unobserved, since no one would be there to measure it. What stays remarkable, whichever explanation eventually proves right, is how much rests on this one faint force. Gravity pulled hydrogen together into the first stars. It pulled those stars into the first galaxies, and slowly, patiently, over billions of years it arranged the raw material for planets and oceans and quiet nights like this one. Somewhere in its almost imperceptible pull lies part of the answer to why anything exists at all. We do not yet know if that pull was chosen, calculated, or simply the outcome of chance in a much larger arrangement of universes. For now, we simply notice that it is there, holding galaxies together across the dark, and holding open a question we have not yet learned how to answer. Let's turn our attention now to a number that touches everything: the speed of light. Physicists write it as a single letter, c, and it moves at about 300,000 kilometers every second. Nothing with mass can go faster. This is not a rule about light alone. It is a speed limit woven into the fabric of space and time itself. Picture a beam of starlight leaving a distant sun. It crosses the dark for years, sometimes for millions of years, before it reaches a telescope on Earth. The light does not hurry. It does not slow down for anything in its path. That steady, unchanging pace shapes how galaxies form, how stars cook their elements, and how energy moves through the emptiness between them. Here is where the mystery begins. The value of c is not just about speed. It appears inside one of the most famous equations in physics, the one that links mass and energy. That equation tells us how much energy is locked inside every bit of matter, from a grain of sand to the iron core of a dying star. If the speed of light had a different value, that link between mass and energy would shift too. Stars might burn differently. They might burn too fast or too slow, or not ignite in a way that builds heavy elements at all. Think about the iron sitting quietly at the center of our planet. It did not come from nowhere. It was forged inside a massive star, cooked slowly over millions of years through nuclear fusion, then scattered across space when that star ended its life in a supernova. That explosion depended on a careful balance of forces, and the speed of light helped set the terms of that balance. Change c, and you change how stars live and how they die. You change whether iron or oxygen or carbon ever get made at all. The oceans on Earth may tell a similar story. One idea suggests that much of our water arrived later, carried by comets and icy asteroids that struck the young planet over and over. Another idea suggests that water was present from the beginning, locked inside the rocky material that formed Earth itself. Either way, the chemistry that holds water together, two hydrogen atoms bound to one oxygen atom, depends on the same physical constants that govern starlight and starlight's speed. Everything traces back to the same small set of numbers. Some researchers wonder whether the speed of light needed to be exactly what it is, or whether a range of values could have still allowed atoms to form and stars to shine. The honest answer is that we are not sure. Small adjustments to see ripple outward into the strength of atomic bonds, into how quickly stars burn through their fuel, into whether a universe stays stable long enough for anything complex to grow. It is a bit like tuning a single string on an instrument and hearing the entire song change shape. There is a competing way to look at this. Perhaps the speed of light only seems remarkable because we exist to notice it. If it were different, perhaps a different kind of universe would form, one without stars like ours, without chemistry like ours, and without anyone around to ask the question. This is sometimes called an anthropic argument, the idea that we should not be surprised to find conditions suited to our own existence, because those are the only conditions in which observers like us could ever appear. It does not explain whether constant has its value. It only asks us to be careful about reading too much meaning into that value. Still, the question lingers in the quiet dark between the stars. Why this speed and not some other? Why a universe where starlight takes just long enough to cross the gap between galaxies, long enough for us to look up and wonder about it? Some physicists suspect a deeper theory, still undiscovered, might one day explain why C must take this value and no other. Others suspect there is no deeper reason at all, that the number simply is what it is, fixed at the birth of the universe by chance or by necessity we cannot yet see. For now, the speed of light remains one thread in a larger pattern, tied to the iron in the ground beneath us, and the water resting in the seas. It moves through the dark at the same steady pace it always has, indifferent to our questions, carrying its secret quietly across the space between everything that exists. Deep inside a red giant star, something quiet and strange is happening. 3 helium nuclei are trying to fuse into a single carbon nucleus. By all rights, this should almost never happen. The chance of 3 particles meeting at once, in the right way, is tiny, and yet carbon is everywhere. It sits in your hands, in the pages of a book, in the breath moving through your lungs right now. Something in the physics of stars makes this rare event common enough to fill the universe with carbon. That something has a name and a story, and it starts with a physicist named Fred Hoyle. In the 1950s, Hoyle looked at the amount of carbon in the universe and found a puzzle. The known nuclear reactions were not efficient enough to produce it in the quantities we see, so he did something bold. He reasoned backward. He said, "We exist and we are made of carbon, so there must be some feature of the carbon nucleus that makes this fusion easier than expected." He predicted a specific energy level inside the carbon nucleus, a kind of internal resonance, a matching of energies between helium and carbon that would act like a door swinging open at just the right moment. Laboratory experiments later found exactly this resonance, close to where Hoyle said it would be. It became known as the Hoyle state, and it remains one of the earliest and clearest examples of what scientists now call anthropic reasoning, using our own existence as a clue about the hidden structure of nature. The resonance works like a tuning fork. When the combined energy of 3 helium nuclei nearly matches the energy of this special carbon state, the fusion becomes far more likely. Push that energy level even a small amount higher or lower, and the door swings shut. Carbon production would drop sharply. Stars would still burn, and helium would still fuse, but the universe would likely end up with far less carbon and far less of the chemistry that carbon makes possible. The same delicate balance also affects oxygen, since carbon can further fuse with helium to make it, if the numbers were only slightly different. The ratio of carbon to oxygen throughout the cosmos might tilt in ways that change what kind of chemistry and what kind of life could ever form. This is where the mystery deepens rather than resolves. Hoyle's discovery shows that the constants governing nuclear forces are tuned finely enough to make carbon common, but it does not tell us why those constants have the values they do. One view holds that this is simply how the numbers turned out, and that we are here to notice it precisely because we needed carbon to exist at all. This is a mild form of anthropic reasoning, and it does not require any deeper explanation. Under this view, asking why the constants are so suited to carbon is a little like asking why we happen to live on a planet with breathable air. Of course we do. We could not be here otherwise. Other researchers find this answer unsatisfying. They point out that the Hoyle state depends on a careful balance between the strong nuclear force and the electromagnetic force, two forces that seem on paper to have no reason to cooperate this well. A small shift in either, one could close the resonance entirely. To some physicists, this near-miss quality, again and again, across many unrelated constants, feels less like coincidence and more like a pattern waiting for an explanation science has not yet found. There is also a quieter question sitting underneath this one. Carbon-based chemistry is the only kind we have ever observed, so it is difficult to know whether other combinations of nuclear forces might allow some different chemistry, built from different elements, to support some different form of complexity. If other stable arrangements are possible, then carbon's fitness might not be as singular as it appears. This possibility remains almost entirely unexplored, since we have no example of a universe built any other way to compare against our own. For now, the Hoyle state stands as one of the clearest windows into fine-tuning that physics has ever found. It shows a real, measurable resonance, discovered through reasoning about our own existence, sitting quietly inside every carbon atom in every living thing. Whether that resonance reflects blind chance, a deeper law we have not yet uncovered, or something about the way observers like us can only ever find ourselves in universes where such resonances exist, remains open. The carbon in your body carries this unanswered question with it, atom by atom, wherever it goes. Let's turn now to a number so strange that many physicists call it the greatest puzzle in all of science. It is called the cosmological constant. It describes something simple. On its surface, it tells us how much energy fills empty space itself. You might think empty space has no energy at all. It looks like nothing. It looks like silence and dark, stretching out forever. But quantum theory, the physics of very small things, says space is never truly still. Even in a perfect vacuum, tiny fluctuations flicker in and out, like static on an old radio. Each of those flickers should carry a little energy. Add them all up, and you get what physicists call vacuum energy. This energy pushes on the fabric of space itself, and that push is what the cosmological constant measures. Here is where the puzzle begins. When physicists calculate how much vacuum energy quantum theory predicts, they get an enormous number. When they measure how much vacuum energy the universe actually seems to have, based on how galaxies drift apart, they get a number close to zero. Not exactly zero, just very, very small. The gap between the prediction and the measurement is not small. It is not even close. It is off by a factor of something like 10, followed by 120 zeros. Let's sit with that number for a moment, because it deserves more than a passing glance. 10 to the 120th power is not a number our minds can hold in any normal way. If you try to write it out, one digit at a time, at a slow and steady pace of 1 digit per second, you would still be writing more than 3,000 years later. If every atom in the observable universe were a single grain of sand, and you piled all of them together, you would still fall unthinkably short of that number. It dwarfs the count of stars, the count of grains of sand on every beach on Earth, the count of seconds since the universe began. Now imagine you had to guess a number between 0 and that unimaginable figure, and the correct answer turned out to be almost exactly 1. That is roughly the situation cosmologists face. The vacuum energy could have taken almost any value across that staggering range. Instead, it landed somewhere small enough that galaxies could form, stars could ignite, and slow, patient chemistry could unfold across billions of years. A slightly larger push from empty space, and the universe would have flown apart before the first stars ever gathered. A slightly different balance, and everything might have collapsed back on itself long before life had any chance to begin. Physicists sometimes describe this as the worst prediction in the history of science, said with a kind of rueful affection, because the mismatch is so total and so strange. It suggests something important is missing from our understanding, some piece of the puzzle we have not yet found. One idea is that some deeper theory, not yet discovered, will explain why the vacuum energy is nearly cancelled out, term by term, through some elegant symmetry we cannot yet see. Another idea, more unsettling to some, is that the value simply is what it is in our particular corner of a much larger structure, and that other regions, other bubbles of space and time, might carry very different values entirely. That second idea leans on the notion of a multiverse, a vast collection of separate universes, each with its own settings for the fundamental constants. If enough of these bubbles exist, then by chance alone, some would happen to have a cosmological constants small enough to allow stars and galaxies and slow-turning planets. We would simply live in one of those. It is a graceful explanation in some ways, but it is also difficult, perhaps impossible, to test. We cannot see beyond our own universe to check. The idea remains a hypothesis, not a confirmed picture of reality. Both explanations leave something unfinished. A deeper theory that cancels the vacuum energy has not been found, despite decades of searching by careful, patient minds. A multiverse that explains the smallness through sheer numbers cannot be observed or verified with the tools we have today. The gap between prediction and measurement stays open, unresolved, sitting there in the equations like a question mark the size of the universe itself. And yet, here we are. The night sky holds its shape. Galaxies drift apart at a gentle, steady pace, not too fast, not too slow. Whatever explains this vast and almost incomprehensible fine balance, it is still waiting for us, somewhere out past what we can currently measure, patient in the dark. Picture a young star still gathering itself out of a cloud of gas. The gas drifts slowly inward, pulled by its own weight, growing denser at the center with every passing 1,000 years. If you could float above this forming star, you would see a dim red glow at its core, wrapped in a haze of falling dust. The surface, if we can even call it that yet, is soft and shifting, more like fog than rock. Nothing is solid here. Everything is still, deciding what it will become. Deep inside that glowing haze, something delicate has to happen. The core must grow hot enough and dense enough for hydrogen nuclei to fuse together into helium. This fusion is what lights a star. It is also one of the most finely balanced events in nature. The strong nuclear force, the same short-range grip we spoke of earlier, that holds atomic nuclei together, has to be tuned just right for that fusion to happen at all. If the strong force were only a little weaker, protons would not bind tightly enough. Fusion would sputter and fail. Stars might never ignite, and the universe would stay dark, filled only with clouds of hydrogen that never learned how to shine. If the force were a little stronger, hydrogen would fuse too easily, burning up in the first moments of the universe. There would be no long-lived stars like our Sun, slowly burning for billions of years, giving planets time to form, and maybe even time for life to begin. Astrophysicist Fred Hoyle noticed a related puzzle in the 1950s when he studied how stars make carbon. He found that carbon nuclei form inside stars through a very specific nuclear step, one that only works because carbon has an energy level tuned almost exactly to match the energy of the particles fusing together. Hoyle predicted this energy level before it was even measured, reasoning that carbon must have it, simply because carbon exists in such abundance in the universe, including inside our own bodies. When the resonance was found, it startled physicists. It also became one of the earliest examples of what scientists now call anthropic reasoning, using our own existence as a clue about the numbers of nature. Some researchers see this as a hint of something deeper, a sign that the constants of physics were somehow selected, tuned, or filtered to allow stars, carbon, and eventually life to appear. Others are more cautious. They point out that a working nuclear resonance in one star process does not prove intention behind the whole universe. It may simply be one of many possible arrangements that happens to permit complexity. Out of a far larger space of arrangements we cannot see or test, standing above one of these newborn stars, if such a thing were possible, you would not see the fusion happening. It occurs invisibly, deep inside the churning core, hidden beneath layers of plasma. What you might notice instead is the star's outer surface beginning to brighten. First a dull ember red, then slowly warming toward orange and yellow as fusion steadies into a stable rhythm. Around it, the last wisps of the birth cloud drift away, pushed outward by radiation pressure, leaving behind clear space and a small, steady light. That steadiness is not guaranteed by just any set of physical constants. It depends on a narrow range of values working together. The strong force, the mass of quarks, the balance between the forces that push nuclei apart and the ones that hold them close. Move any of these values by a small amount in either direction, and the balance seems to tip toward a universe of failed stars, or no stars at all. The open question is why this balance exists. One idea is that we are witnessing pure chance, one lucky roll among many, no more meaningful than a snowflake's particular shape. Another idea holds that vast numbers of universes exist with different constants, and we simply find ourselves in one where stars can ignite, because only such a universe could contain someone to notice. A third possibility, still speculative, is that some deeper physical law fixes these values necessarily, and there was never any other way for them to be. No experiment yet tells us which of these is true, or whether some other explanation waits undiscovered. For now, we can only watch the stars form, glowing softly against the dark, and wonder at how easily their light could have never happened at all. Somewhere above a quiet planet, one of those stars is rising right now, its fusion still running on the same delicate balance, still holding steady, still unexplained. Deep in the early universe, long before any star had lit its first fire, there was a ratio quietly holding everything in place. For every 1 billion antimatter particles, there were 1,000,000,001 particles of matter. That single extra particle out of a billion is the reason anything exists at all. Picture it slowly, the way you might picture snow falling in a still, dark field. In those first fractions of a second after the beginning, matter and antimatter were created together in pairs, like mirror images facing each other. When a particle met its antimatter twin, both vanished, turning into pure light. Almost everything vanished this way. Almost. If the early universe had been perfectly balanced, with equal amounts of matter and antimatter, every single particle would have found its twin. Every one would have annihilated into light. There would be no galaxies, no stars, no dust settling into planets, no quiet body lying in a bed, listening to this voice. Just a smooth, silent bath of photons, expanding forever into the dark, warm but empty, glowing but hollow. Instead, that tiny surplus, 1 part in a billion, survived the great annihilation. That leftover matter is what makes up every star, every moon, every breath you take tonight. Physicists call this puzzle baryon asymmetry, the unexplained tilt between matter and its opposite. Baryons are simply the heavier particles, like protons and neutrons, that make up the ordinary stuff of the world. The asymmetry is the imbalance between them and their antimatter counterparts, and here is the part that still keeps researchers wondering. Nothing in the basic equations of physics demands that this imbalance should exist at all. The known laws treat matter and antimatter almost as equals, like two dancers in perfect step. Some very small differences have been measured in laboratories, tiny preferences shown by certain particles for matter over antimatter. But when researchers add up these known effects, they fall short. They are nowhere near enough to explain the surplus we observe. Something else, some process still unaccounted for, seems to have tipped the scale in favor of existence. One leading idea points to the earliest moments of the universe, when conditions were violent and strange beyond anything we can recreate. Some researchers propose that heavy, unstable particles existed briefly then, decaying in ways that favored matter just slightly. Others wonder if the answer lies with neutrinos, the ghostly particles that pass through planets without notice, and whether their behavior in that first instant nudged the balance. Both ideas remain unproven. Neither has been confirmed by direct observation. What makes this particular constant so unsettling, in the gentlest sense of the word, is how narrow the margin was. If that surplus had been smaller, matter might have been too sparse to pull together into stars. Gravity would have had too little to work with, too few particles scattered across too much space. If the surplus had been larger, some models suggest the early universe might have been so dense with matter that it collapsed too quickly before galaxies had time to spread and settle into their slow, patient shapes. This is where the ratio of matter to light becomes part of the larger question this episode is sitting with tonight. It is not only that the numbers work, it is that they work within a strangely thin range, a range that seems to have been threaded like a needle through overwhelming odds. Some see this as a hint that our universe may be one of many, a vast and unseen collection where most versions never balanced correctly, and ours simply happened to. Others see it as a sign that some undiscovered piece of physics, some deeper symmetry breaking, made the surplus close to inevitable once the right conditions were in place. Neither view can be tested completely, not yet. The instruments that might catch the faint fingerprints of that first imbalance are still being built and refined, tucked into deep underground laboratories, dark and cold and quiet, listening for particles that rarely speak. For now, the ratio remains a beautiful, outstanding question, written in the proportion of light to matter, drifting across every photograph of the night sky, every photon that reaches your eyes from a star, and every atom in your own body are both echoes of that same ancient imbalance. They are two sides of the same untold story, one that turned into starlight, the other into everything solid enough to wonder about it. The universe kept just enough matter to build itself a home. Why it kept that much, and not more, and not less, is still an open door, standing quietly in the dark. Let your mind rest on something small tonight, an atom, a quiet arrangement of electrons circling a nucleus, over and over, without ever wearing out or falling apart. This steady repetition is one of the strangest gifts hidden inside the universe's constants. Atoms hold their shape for billions of years, cycling in the same patterns, and that stability is not something we should take for granted. Picture an electron moving around a hydrogen nucleus. It does not spiral inward and crash. It does not drift away and disappear. It settles into a rhythm, a repeating orbit that seems to know exactly how far to stay and exactly how fast to move. This balance depends on a number called the fine structure constant, which measures how strongly light and matter interact with each other. It sits close to 1 part in 137, a strange quiet fraction with no obvious reason for that particular size. If this number were even slightly different, the whole rhythm would change. A stronger pull between electrons and nuclei would crush atoms into tighter, less stable shapes. A weaker pull might let electrons drift so loosely that atoms could barely hold together at all. Chemistry, as we understand it, depends on this careful cycling staying exactly where it is. Molecules could not form, bonds could not repeat in the same reliable way from one atom to the next. Some physicists see this as a hint of something deeper, a fine-tuning that allowed matter to settle into steady repeating patterns instead of chaos. Others see it as one part of a much larger set of coincidences that only look special because we exist to notice them. Both views sit inside the same open question. Neither one has been shown to be the full answer. There is a comfort in this kind of cycling. Think of the way seasons turn, or the way tides rise and fall along a shore. Atoms do something similar, on a scale far too small to see, but just as rhythmic. Electrons complete their orbits again and again, never breaking their pattern, never skipping a beat. This tiny, endless repetition became the foundation for everything solid in the universe, from mountains to bones to the page of a book. If the strength of this atomic dance had wandered even a little from its narrow range, stars might have burned differently, and the elements needed for planets might never have formed properly. Some physicists describe this as walking a tightrope, where a small shift in either direction changes the outcome completely. Others caution that we do not yet know how much shifting the constant could take before atoms simply reorganize into some other stable form we have not imagined. The boundaries of that tightrope remain uncertain. This uncertainty is part of what makes the mystery so quiet and so deep. We are not just asking why atoms are stable. We are asking why the specific rhythm that holds them together happens to match a range that allows chemistry and stars and slow, patient cycles of formation across billions of years. It is easy to imagine other numbers that might have led to a universe with no atoms at all, or atoms too fragile to form anything lasting. Some researchers wonder whether these atomic cycles are echoes of something larger, patterns that repeat because the universe itself favors certain kinds of stability. Others argue that we simply live inside the range that permits observers to exist, and that any other range would leave no one around to ask the question. Both explanations remain open, resting side by side without resolution. There is something soothing in imagining these tiny orbits repeating endlessly in the dark, undisturbed, keeping their shape while galaxies drift and stars flicker out overhead. The atoms in your own body have been cycling this way since long before you were born, holding their quiet rhythm through eras of cosmic history none of us witnessed. It is a small, steady kind of permanence, hidden inside a universe that otherwise seems so vast and changing. As you rest tonight, you might picture that soft orbital hum inside every atom around you, a cycle so old and so fine-tuned that its origins remain unexplained. We do not know why this rhythm holds so precisely, or whether other rhythms could have worked just as well in some other universe we cannot see. The pattern continues, faithful and unbroken, asking its quiet question long after we have stopped paying attention. Somewhere between physics and wonder, the mystery waits, patient as an atom completing another slow, unnoticed turn. There is a number in physics with no units at all. It has no meters attached, no seconds, no kilograms. It is just a number, pure and small, sitting quietly at about 1/137. Physicists call it the fine structure constant, and it measures how strongly light and matter talk to each other. Picture an electron circling close to the heart of an atom. The fine structure constant tells you how tightly that electron is held, how strongly it feels the pull of the charged nucleus nearby. It shapes the size of every atom. It shapes the color of every flame. It shapes the way light bends when it passes through glass, and the way a rainbow spreads its colors across a wet sky after rain. Nudge this number even slightly, and chemistry itself begins to change shape. If the fine structure constant were a little larger, electrons would be pulled in more tightly, atoms would shrink. The bonds between atoms, the delicate handshakes that hold molecules together, would grow stronger and stiffer in some cases, and impossible in others. Some researchers who have modeled these changes suggest that stars could still burn, but the chemistry needed for anything like life may become far more narrow or vanish completely. If the constant were smaller, the opposite kind of trouble appears. Electrons would drift farther from their nuclei, atoms would puff outward, bonds would loosen, and the stable architecture that builds proteins, rocks, and oceans could come undone. The number seems to sit in a narrow, comfortable middle ground, neither too tight nor too loose, and no one can fully explain why it landed there. This is where the idea of neighbors becomes useful. No constant in physics stands alone in an empty room. The fine structure constant is built from other pieces, including the electron's charge, the speed of light, and a small quantity called Planck's constant, which sets the smallest meaningful scale of energy and action in the universe. Change one neighbor, and the whole number shifts because they are woven together in the same equation. It is a bit like a garden where every plant depends on the soil moisture set by the plant beside it. Pull one root, and something nearby feels it too. This is part of why physicists find fine-tuning so difficult to study in isolation. You cannot simply ask, what happens if you turn one dial, while leaving every other dial untouched? Because in the real equations, many of these dials seem to be connected under the surface. Some researchers wonder if there is a deeper, still undiscovered relationship binding these constants together, something that would explain why they cluster near life-permitting values instead of being independent numbers, each rolled separately by chance. Others are cautious about this idea, noting that we have no confirmed theory that links them this way yet. It remains a hope, not a result. There is also the question of how much room these numbers actually have to move before something breaks. Some physicists who have run calculations suggest the fine structure constant could wander only a small percentage from its current value before the chemistry of carbon and oxygen becomes unstable in stars. Other researchers caution that these calculations rest on simplified models, and the true tolerance might be wider or narrower than anyone has yet shown. The boundary of safety, if there even is a single clean boundary, has not been fully mapped. A separate mystery sits quietly beside this one. Some astronomers have looked at light from distant quasars, ancient beacons from the early universe, hoping to see if the fine structure constant might have drifted even slightly over billions of years. A few early studies hinted at tiny shifts. Later, more careful studies found no clear drift at all, within the limits their instruments could measure. The current evidence leans toward the constant, but the measurements are difficult, and the door has not fully closed. What makes this particular number so quietly unsettling is how ordinary it feels in daily life, and how strange it becomes under examination. It is present in the glow of a candle, the transparency of water, the blue of a butterfly's wing, and yet, trace it back far enough, and you find a bare number with no explanation for its size, sitting at the center of every chemical bond ever formed. We do not know why it favors complexity so gently, instead of forbidding it outright. We do not know if some undiscovered structure quietly pins it in place. For now, it remains one neighbor among many unexplained neighbors, each one leaning on the others, each one holding up a little more of the improbable architecture we happen to live inside. Let's turn now to the strangest number in all of physics. It is a number so small and so strange that some scientists have called it the worst prediction ever made. It concerns something called dark energy and the quiet, steady push it seems to give to the universe. Picture the darkness between galaxies. It looks empty, it looks still, but something in that emptiness is pushing outward, gently stretching the space between every cluster of stars. We call this dark energy. We do not know what it is made of. We only know its effect, measured by watching distant supernovae fade with a certain pattern of light. The universe is not just expanding, it is expanding faster with each passing age. Physicists gave this pushing force a number. They call it the cosmological constant, and it represents the energy held within empty space itself. Here is where the puzzle deepens. When theorists calculate what that number should be, using the equations of quantum theory, they get a value so large it would tear galaxies apart before they ever formed. Yet, when astronomers measure the number using telescopes, they find something almost impossibly small. The gap between the predicted number and the observed number is not small. It stretches across some 60 orders of magnitude, a difference so vast it is hard to picture. Imagine expecting an ocean and finding a single drop. That gap is one of the deepest open wounds in modern physics. Some researchers wonder if we are simply missing a piece of the puzzle, some deeper cancellation in the mathematics that quietly removes almost all of that predicted energy, leaving only the faint whisper we observe. Others wonder if the smallness itself is the real clue, a sign that something in our understanding of gravity or quantum theory needs to change at its root. No one has found the missing piece yet. The disagreement between prediction and measurement remains unresolved. Sitting quietly at the center of cosmology like an unopened letter. There is another way of looking at this mystery, and it returns us to the question of fine-tuning that runs through this whole story. If the cosmological constant had been only slightly larger, space would have expanded so quickly that matter could never have clumped together. Stars would not form, galaxies would not form. Structure of any kind would have been smoothed away before it had a chance to begin. If the constant had been negative and slightly larger in the other direction, the universe might have collapsed back on itself long before life had any chance to arise. The actual value sits in a narrow window that allows both expansion and structure to coexist. Some call this a second layer of fine-tuning, stacked on top of the fine-tuning we already find in the forces that hold atoms together. One idea, drawn from the same well of thinking that explains other constants, suggests that many regions of space, or many separate universes, might carry different values of this energy. In such a picture, only the regions where the number lands in that narrow habitable window would ever develop galaxies, stars, and eventually eyes to look up and wonder. We would find ourselves in such a region simply because we could not exist anywhere else. This is a form of the anthropic reasoning we touched on earlier, applied now to the very fabric of empty space. It offers no proof, only a shift in framing, and many physicists remain uneasy leaning on it as a full explanation. Others hold out hope for something more direct, perhaps a future theory, one that finally joins gravity with the quantum world, will show that this value was never a coincidence at all. Perhaps it follows from some deeper structure we have not yet found, the way the orbits of planets once seemed mysterious, until Newton showed they followed simple laws of motion. That kind of theory does not exist yet. Every attempt so far has run into the same wall, the same enormous gap between prediction and observation. For now, the number remains what it is, measured with care, unexplained in its size, and strangely well suited to a universe that contains stars and dust and thinking creatures who wonder about such things. Whether that fit is coincidence, necessity, or something we simply cannot see the reason for, yet remains open. The push behind the darkness continues, silent and immense, carrying galaxies gently apart, while we search for a reason we may or may not ever find. Let's turn our attention to something almost too small to picture. The electron, that tiny particle circling every atomic nucleus, weighs almost nothing. Its mass is a little over 500,000 electron volts, a unit physicists use for things this small. Next to a proton, the electron weighs about 1/1800th as much. It is a whisper of a particle, nearly weightless by the standards of ordinary matter. And yet this whisper shapes almost everything you can touch, smell, or taste. Chemistry happens because electrons are light. They move fast around the nucleus, fast enough to form the shells and orbitals that give atoms their shape. If electrons were heavier, they would sit closer to the nucleus, held tighter by its pull. Atoms would shrink. The gentle give and take of chemical bonds, the sharing of outer electrons between atoms, would change in ways chemists still find hard to fully model. Some researchers wonder whether molecules as complex as proteins or DNA could form at all if this one number were different. There is a companion number worth sitting with here too, the mass ratio between the electron and the proton. Physicists call it mu, a small Greek letter standing in for a very particular fraction. That fraction is close to 1 part in 1800, and it shows up again and again in the equations that describe how atoms vibrate, how molecules bend and stretch, how starlight gets absorbed by gas clouds between the stars. Change that ratio even slightly, and the small vibrations inside molecules shift too. Some theorists have studied how this would alter the chemistry of stars, the cooling of gas clouds, even the way planets might form around them. The models suggest that a universe with a different ratio could still have physics, but it might not have the same slow, steady chemistry that lets planets cool, oceans settle, and long molecules link into chains. Here is where the wonder deepens rather than resolves. Nobody knows why the electron has the mass it does. It is not calculated from some deeper law we have found. It is simply measured, over and over, in laboratories around the world, and it always comes back the same. Physicists sometimes call numbers like this free parameters, meaning the current theories allow almost any value. Yet the universe seems to have picked one very specific value and stuck with it. Some physicists find this troubling in a quiet way, the way a puzzle piece that fits perfectly might make you wonder if someone shaped it on purpose. Others see it differently. They point out that many combinations of particle masses might allow some kind of complexity, just not the kind we recognize as life. We may be noticing this one value simply because it is the one that allowed noticers to exist. That idea, sometimes called observer selection, does not explain why the electron has this mass. It only explains why we, the observers, happen to find ourselves in a universe where it does. There is also the question of drift. Could the electron's mass have been different in the early universe and slowly settled into its current value over billions of years? So far, precise measurements of atomic spectra, the fingerprints of light that atoms give off, show no sign of change over cosmic time. There, the number appears steady, at least within the limits our instruments can detect. Whether it has always been steady, or whether it simply changes too slowly for us to notice yet, remains an open question researchers continue to test. What makes the electron's mass feel different from the larger forces we have already wandered through is its intimacy. Gravity shapes galaxies. The strong force holds nuclei together across the universe. But the electron's mass touches something closer to home, the chemistry inside your own body, the bonds holding together the very cells. Doing the reading of this sentence, if you are still awake enough to follow it. It is a small number with an outsized reach, one thread among many, stitched into the same unresolved of coincidence or necessity. Physicists have not stopped hunting for a deeper reason. Some hope a future theory, one that unifies the forces of nature into a single framework, might reveal why the electron's mass sits exactly where it does, tied to some symmetry of pure mathematics, still hidden from us. Others suspect there may be no deeper reason at all, that the value is simply a fact about our particular universe, the way one house happens to be painted blue instead of green. For now, the electron drifts through its orbits, wakeless and essential, and the question of why it weighs what it weighs drifts along with it, unanswered, patient, waiting quietly in the dark for someone, someday, to notice the missing piece. Picture the universe in its first fraction of a second. It is smaller than a grain of sand, hotter than anything that will ever exist again, and expanding at a rate no one has ever measured directly. Somewhere in that tiny fire, two forces are pulling in opposite directions. Gravity wants to pull everything back into a single point. Expansion wants to fling everything apart so fast that no matter ever gets a chance to gather into stars. For a long time, physicists studying the early universe kept running into the same puzzle. The rate of expansion in those first moments seems to have been tuned with almost impossible precision. If the early universe had expanded even slightly faster, matter would have spread too thin. Atoms would have drifted apart before gravity ever had a chance to pull them into clumps. No clouds of gas, No stars, no galaxies, just a thin, cold mist of particles scattered forever across an ever-widening dark. If the expansion had been even slightly slower, the opposite would have happened. Gravity would have won early and fast. The whole universe would have collapsed back on itself, likely within minutes, long before atoms could even form. Some researchers have described this balance as sitting on a razor's edge, though it might be gentler to say it looks like a coin standing on its side, one that somehow never fell either way. This puzzle became sharper in the 1980s, when cosmologists tried to work out just how finely balanced that early expansion rate needed to be. The numbers that came out of those calculations were startling. Some estimates suggested the balance between expansion and gravity in the early universe needed to be accurate to within 1 part in many trillions. Even a whisper of difference in either direction seems to lead to a universe without anyone in it to notice. The scientists who worked on this were not exploring with telescopes. They were exploring with equations, tracing the universe backward through time, using the physics of general relativity, the theory that describes how mass and energy bend space itself. They found that the early universe's flatness, meaning how evenly balanced its geometry seems to be between expanding forever and collapsing, was one of the strangest details in all of cosmology. Flat space is possible, but nothing in the equations demanded it. It just happened to come out that way. One idea that emerged to explain this is called cosmic inflation, a theory suggesting the universe went through a burst of extremely rapid expansion in its first fraction of a second. Under this idea, whatever the starting conditions were, that fast stretching would have smoothed things out and pushed the universe toward flatness almost automatically, the way stretching a wrinkled balloon flattens out its surface. Inflation remains one of the best supported explanations cosmologists have. But it is not the end of the story. Inflation still needs its own finely tuned starting conditions to work the way it does. And physicists have not agreed on why those conditions existed either. Not every researcher is convinced that inflation solves the deeper puzzle. Some see it as pushing the question back a step, rather than answering it fully. Others wonder if this apparent balance is less mysterious than it seems, since only a universe with this kind of balance would ever produce anyone able to ask about it in the first place. That idea, called anthropic reasoning, does not explain why the balance exists. It only reminds us that we could not be here to wonder about it if it did not. What makes this moment in cosmic history so quietly astonishing is how little room there was for error. This was not a slow negotiation between forces over millions of years. It happened in the first instance of existence, faster than the blink of anything with eyes to blink. And somehow, whatever set, the terms of that instant left just enough room for matter to survive long enough to become stars and planets, and eventually someone lying in the dark, wondering how any of this held together. No one alive to study this moment watched it happen. There were no instruments, no telescopes, no ships crossing dark water to observe it firsthand. All we have are the equations, the leftover light from long ago, and the quiet, persistent question of why the numbers came out just narrow enough to allow for a universe like this one. The early universe did not collapse. It did not disperse into nothing. It simply held in a way that still resists a complete explanation, and became the sky above us tonight. Picture a single drop of water resting on a leaf, catching the last light of evening. It looks ordinary. It looks like the simplest thing in the world. And yet water breaks almost every rule that other liquids follow, in ways that happen to make life possible. Most liquids get denser as they cool. The colder they get, the tighter their molecules pack. all the way down to the point where they freeze solid. Water does this too for a while. But somewhere around 4 degrees Celsius, water changes its mind. It starts to expand again as it approaches freezing, so that ice, solid water, is less dense than the liquid beneath it. This is why ice floats. It sounds like a small detail. It is not. If ice sank instead of floating, lakes and oceans would freeze from the bottom up. Ice would pile onto the floor of every sea, layer after layer, winter after winter, never fully melting. Even in summer, entire bodies of water could freeze solid over time. Some researchers who study early Earth think this single property may have kept oceans liquid enough, long enough, for the first chemistry of life to unfold. Without it, the story might have gone very differently. The reason for this strange behavior lies in the shape of the water molecule itself. 2 hydrogen atoms bond to 1 oxygen atom, but not in a straight line. They meet at a bent angle, close to 105 degrees. That bend gives the molecule an uneven distribution of charge, one side slightly positive, the other slightly negative. This is what chemists call polarity, a kind of built-in magnetism at the molecular scale. Because of it, water molecules pull toward each other in a loose, shifting web called hydrogen bonding. When water freezes, those hydrogen bonds lock into a 6-sided lattice, an open, airy structure with more space between molecules than the liquid has. That extra space is why ice takes up more room and why it floats instead of sinks. Warm the ice back up, and the lattice collapses. Molecules crowd closer, and the liquid becomes denser again. This whole sequence depends on the precise bend of the molecule and the precise strength of the electric forces holding it together. Values set, ultimately, by the fine structure, constant, and the mass of the electron. Numbers we touched on a little earlier tonight. Water carries other quiet oddities too. It takes an unusually large amount of energy to heat it up. Compared to most liquids of similar size, oceans and lakes hold on to warmth through the night and release it slowly, softening the swing between day and night, summer and winter. Some climate researchers point to this heat capacity as one reason Earth's surface temperatures stay gentle enough in most places for liquid water to persist year-round. Planet covered in a liquid with different thermal properties might swing between extremes, too sharp for stable chemistry to take hold. None of this proves that water was designed for life, and no serious researcher claims that it was. One view holds that water is simply what you get when hydrogen and oxygen, 2 of the most common elements in the universe, combine under normal cosmic conditions. Life, in this view, did not need water specifically. Life adapted to whatever solvent happened to be abundant and stable enough to work with. If Earth's chemistry had produced oceans of ammonia or methane instead, perhaps a different kind of biology would have found a way to use those liquids just as well. A different view leans further into the coincidence. It notes that water's oddities are not just convenient, but oddly numerous, each one tracing back to constants that could, in principle, have taken other values, changed the strength of the electric force only slightly, and the hydrogen bond weakens or vanishes, and water behaves like an unremarkable liquid that sinks solid and offers little thermal comfort. Whether this counts as evidence of something deeper, or simply the outcome of ordinary chemistry playing out over billions of years, remains an open question, with no clear way to settle it. What stays remarkable, whichever view feels more convincing, is how many separate details had to line up. The bend of a molecule, the reach of a bond, the number that sets how strongly opposite charges attract. Each one plays a part in something as familiar as a floating piece of ice on a summer pond. Tonight, there is no need to resolve which explanation is right. It is enough to notice that the water in every glass, every cloud, every quiet tide carries a small, unfinished mystery inside it. Let's step back for a moment. We've looked at carbon, water, gravity, and light, one at a time, like beads on a string. But there is another way to hold this mystery. Instead of asking whether each constant is tuned, we can ask whether we are the ones doing the tuning, simply by noticing anything at all. This is the heart of an old and quiet debate. Some physicists look at the long list of lucky numbers and feel a pull toward wonder, even toward design. Others look at the same list and feel a pull toward caution. They ask a simple, almost deflating question. Of course, the constants allow observers to exist. If they did not, there would be no one here to measure them. This idea has a name. It is called observer selection, and it is closely related to something called the Anthropic principle, which we will sit with more fully in a later section. For now, think of it like this. Imagine a fish that could only ever live in water of a very exact temperature. If that fish woke up one day and marveled at how perfectly the ocean suited its needs, we might smile gently. The ocean was not built for the fish. The fish simply could not exist anywhere else. Some researchers wonder if we are doing something similar when we marvel at the strength of gravity, or the mass of the electron, or the strange near-zero value of the cosmological constant. We are here, we are looking. Of course, the numbers we find are numbers that allow looking to happen. Under this view, fine-tuning is not a signal pointing towards some deeper purpose. It is closer to a kind of mirror, reflecting our own condition back at us. But this answer does not satisfy everyone, and the disagreement itself is part of the mystery. A common objection goes like this. Observer selection can explain why we do not find ourselves in a universe with no stars. It does not fully explain why the deep structure of physics allowed for a universe with stars in the first place. There is a difference between saying we would not notice a lifeless universe and explaining why a life-permitting universe exists to be noticed at all. The first is almost a truism. The second still feels like a real question, one that observer selection alone may not answer. Think of it this way. If someone deals you a hand of cards and it happens to be a royal flush, you can say, "Of course I am holding this hand, since I am the one who was dealt it." That is true, but it does not explain why the deck was arranged so that a royal flush was even possible to draw. Something still produced the deck. Something still shuffled it, or did not shuffle it, in just the right way. This is where the different threads of the episode begin to touch each other. The carbon resonance that Fred Hoyle predicted connects to the strong force holding nuclei together. The strong force connects to how stars burn and how heavy elements form. Heavy elements connect to rocky planets, and rocky planets connect to the chemistry of water we explored earlier. Pull on any one thread, and the others move with it. The universe's constants do not sit in separate boxes. They lean on each other, like players in a very quiet orchestra, each one shaping what the others are allowed to do. Seen this way, the fine-tuning question is not really about a single lucky number. It is about how an entire interlocking system of numbers seems to cooperate. Some physicists suspect this cooperation points to a deeper, undiscovered rule, some hidden principle that forces the constants to take the values they have. Others suspect there is no deeper rule at all, and that we simply live inside one workable arrangement among many that might have existed, observed only because it happened to allow observers. Neither position has been proven. Neither has been ruled out. The debate is not settled by evidence, so much as by which kind of explanation feels more satisfying, more complete, less like a shrug dressed up as an answer. That tension between wonder and caution, between design and selection, is not a flaw in the science. It is simply where the science currently stands. For tonight, you do not need to resolve it. You can simply notice how connected everything is, how one constant leans quietly against the next, holding up a universe that permits stars, oceans, and someone lying still in the dark, listening, wondering how all of it came to fit together so well. Picture a shoreline with an endless number of waves, each one rising, curling and falling back into the sea. No two waves are exactly alike. Some are small ripples, some are towering walls of water. Now imagine that each wave is not water at all, but a universe, complete with its own version of gravity, its own strength of the nuclear force, its own value for the cosmological constant. This is the rough shape of one idea that tries to answer why our universe seems so finely balanced. It is called the Multiverse, and it suggests that our universe might be only one wave among countless others. The reasoning goes like this. If the constants of physics could have taken many different values, and if some process in nature generates universes with different combinations of those values, then it stops being strange that we find ourselves in one that works. A universe where the strong force was too weak to hold nuclei together would have no stars, no chemistry, and no observers. A universe where the cosmological constant was too large would fly apart before a single galaxy could form. In a landscape of many universes, the ones with the right numbers are simply the ones that end up with someone around to notice. We are not lucky. We are just the sample of the population that could ask the question at all. This idea does not come from nowhere. Some versions of it emerge naturally from certain models in cosmology, including inflation, the theory that describes a burst of extremely rapid expansion in the earliest fraction of a second after the Big Bang. In some inflationary models, this expansion never fully stops. Instead, it continues in patches, spinning off separate bubbles of space, each one settling into its own set of physical constants as it cools. String theory, an unfinished framework that tries to describe all matter and forces as vibrations of tiny strings, adds another layer to this picture. Some versions of string theory predict a vast number of possible stable configurations, each one describing a universe with different physical laws. That number is sometimes estimated at 10 raised to the 500th power or more, though it remains a mathematical estimate, not an observation. The trouble, and it is a real trouble, is that none of these other universes can be seen, touched, or measured, even in principle, by any instrument we know how to build. They lie beyond our cosmic horizon, the boundary past which light has not had time to reach us since the beginning of the universe. A theory that cannot be tested sits in an uncomfortable place in science. It might be true. It might explain everything, but without a way to check it, it risks becoming a story that fits the facts, because it was built to fit the facts, rather than a story that predicts something new. Not every physicist finds comfort in the multiverse. Some prefer a different kind of hope, one where a deeper theory, still undiscovered, will eventually explain why the constants had to take the values they have, with no other option ever available. In that view, our universe is not one lucky wave among many. It is the only wave the ocean could ever produce, because the ocean itself has no other way to move. This would mean fine-tuning is an illusion created by our incomplete understanding, not evidence of chance or selection at all. So far, no one has found that deeper theory, though many have searched. there is also a quieter, stranger possibility worth sitting with. Perhaps the multiverse is real, but the process that generates new universes is not random. The physicist Lee Smolin once proposed an idea called cosmic natural selection, where universes might reproduce through black holes, and the resulting offspring inherit constants close to their parents with small variations. Over immense stretches of time, this could favor universes that are especially good at making black holes, which happen to require conditions not unlike the ones that also make stars, carbon, and perhaps life. Yet, it is a speculative idea, tested against very little evidence, but it shows how many different shapes this mystery can take. None of these possibilities has been confirmed. None has been ruled out. The multiverse remains one candidate answer among several, resting on models that are mathematically interesting, but observationally silent. It offers a way to make our universe's strange balance feel ordinary. One wave among countless waves, rather than a single improbable arrangement, whether that comfort is earned, or whether it simply moves the mystery one step further out of reach, is something even the physicists who study it continue to quietly debate. Picture the light of a single star, traveling for years through the dark, until it lands on your eye as a point of gentle color. That light carries information about the atom that made it. Every glow in the night sky, from the faint red of a cooling ember of a star to the hard blue-white of a young giant, comes from constants doing exactly what they do, everywhere, without exception. The color of starlight is, in a way, a fingerprint of the numbers that built it. Think about the blue of an afternoon sky, back when there were afternoons to watch. That blue exists because of how light scatters through gas, a process governed by the same fine constants we have been circling all night. Change the strength of the electromagnetic force, even slightly, and every color in the universe would shift. The gold of sunset, the pale glow of moonlight on snow, the way lava glows orange as it cools and dims to red. All of it depends on rules that seem to have been set with unusual precision. This brings us to a quiet, patient question. Could those rules have been set differently? Could there be some other combination of constants, some other version of the physical rulebook that would also allow atoms to form, light to shine, and something like a mind to look up and wonder about it? Some physicists think the answer might be yes, at least in a narrow sense. Small adjustments to certain constants, paired with compensating adjustments elsewhere, might still produce workable atoms and stable stars. In this view, our universe is not the only possible winning ticket. It may be one of many, sitting somewhere in a wide field of numbers that could each support their own kind of complexity, their own kind of glow. Other physicists are far less convinced. Many of the fine-tuning examples we have walked through, the strength of the strong force, the near cancellation in the cosmological constant, the resonance that lets carbon form inside stars, seem to sit on narrow ledges. Nudge them even a little, and the ledge disappears. In this stricter view, our particular set of numbers is not just one workable option among many. It might be a rare and isolated point of balance, surrounded on all sides by universes that go dark, or collapse, or never form structure at all. No one has been able to fully map this space of possibilities. We do not have a working theory that lets us dial the constants up and down and simply watch what happens. What we have instead are approximations, thought experiments, careful calculations, done with pencil and patience, each one exploring a single what-if while holding everything else fixed. That is useful, but it is not the same as truly knowing the full shape of what could have been. There is something almost visual about this uncertainty. If you let yourself picture it, imagine a vast dark field scattered with faint points of light, each point representing one possible universe, defined by one possible set of constants. Most of the field is truly dark, universes where atoms never held together, where stars never lit, where nothing like a nebulous soft color ever formed. Somewhere in that field is a single glowing point, ours, bright enough to cast starlight across billions of years, bright enough for us to be here noticing it. Whether that point is one of many similarly bright points, or nearly alone in the dark, remains an open question. The honest answer tonight is that we do not know how many of those other points would glow, if they exist at all, outside of thought experiments and equations. We do not know if the deep blue of a planet's sky, the pale shimmer of ice on a frozen moon, or the slow orange pulse of a dying star are common outcomes across many possible physics, or rare and precious accidents of this one. The light we see is real, and it is beautiful, but the reasons behind its particular colors, its particular physics, are still being worked out on chalkboards and in quiet conversations among people who study these things for a living. For now, we can simply notice the glow. We can notice that it exists at all, spilling gently across the dark, painted in colors that depend on constants we did not choose and cannot yet fully explain. Whether those colors were inevitable, or whether they are one lucky arrangement among countless silent, unlit possibilities, is a question that light itself cannot answer. It can only carry the evidence to us patiently across the years and let us wonder. Space itself makes no sound. There is no air out there to carry a wave, no medium to shake and ripple the way a drum skin shakes. And yet, if you listen closely to the instruments we send into the dark, you find something like sound waiting to be uncovered. Plasma hums around planets, radio emissions from Jupiter, converted into audio, crackle and whistle like something almost alive. Gravitational waves, ripples in space itself, can be translated into a soft chirp, a rising tone that lasts a fraction of a second. These sounds are borrowed, translated from vibrations no ear could ever hear directly. They remind us that the universe is full of motion we can only sense indirectly, through instruments that stand in for our own limited senses. The Anthropic principle asks us to listen in a similar way, translating a silence into something meaningful. It does not measure a wave or a hum. It starts from a simple observation. We are here, asking questions, and that fact alone tells us something about the kind of universe we must live in. If the constants had been very different, there would be no atoms, no stars, no observers to wonder about any of it. So in one sense, the fact that we can ask the question already answers part of it. We exist in a universe that permits existence. That statement sounds almost too simple to matter, and there the trouble begins. Physicists have split this idea into two versions, sometimes called weak and strong. The weak Anthropic principle says only that any observer will necessarily find themselves in conditions that allow observers to exist. It is a statement about selection, not causation. Out of all the possible universes, or all the possible regions of one very large universe, we would only ever find ourselves in a place suited to us. That is not mysterious. It is closer to a tautology, a statement that is true simply by its own definition. Many physicists accept the weak version without much argument, treating it as a useful reminder rather than a discovery. The strong version reaches further and says the universe must have properties that allow observers to eventually appear, as though life or mind was somehow necessary to the cosmos, rather than an accident within it. This version makes some scientists uneasy. It edges toward the idea that the universe was built with a purpose, or that observers play a role in bringing the universe into being at all. An idea drawn from certain interpretations of quantum mechanics. Other physicists see this as stretching a modest observation into something closer to philosophy than physics. The disagreement between these two versions has never fully settled, and each side hears the same silence and describes a different sound. Skeptics of the anthropic approach raise a pointed question. If the principle only tells us that we observe conditions suited to observers, does it explain anything? Or does it simply describe the obvious without adding new information? A theory earns its place in science partly by predicting something we did not already expect, something that could, in principle, turn out false. Critics ask whether the anthropic principle could ever be shown wrong, or whether it quietly avoids that test altogether. Supporters answer that it can make a kind of prediction after all. It suggests that if a vast number of regions or universes exist with differing constants, most observers should find themselves near the more common ranges compatible with life, not at some rare and extreme edge. Whether we can ever measure such a range remains an open and difficult problem, since we only have one universe we can observe directly. There is a quieter version of this idea worth sitting with. Perhaps the anthropic principle is less an explanation and more an honest confession of our limits. We hear the universe only through the instruments we have built and the questions our minds are shaped to ask. Just as those Jupiter radio bursts only become sound once we choose to convert them, our sense of fine-tuning may say as much about how we interpret the numbers as about the numbers themselves. Some researchers wonder if we are hearing a genuine signal about the structure of reality. Others wonder if we are only hearing the echo of our own presence, bouncing back at us, disguised as a mystery. No one has closed this question. The universe continues its long, silent hum, indifferent to whether we call it evidence or coincidence. We are left turning the strange quiet into meaning, the same way we turn a gravitational ripple into a chirp, hoping that somewhere in the translation we have not invented the very thing we are trying to hear. Somewhere beneath the list of constants, physicists keep asking a quieter question. Are these numbers truly separate from each other? Or are they all shadows of one deeper pattern we have not yet found? The strength of gravity, the mass of the electron, the pull that holds a nucleus together. What if they are not 20 different settings on 20 different dials, but expressions of a single, simpler rule written in a language we are still learning to read? This hope has a name. Physicists call it a unified theory, a single mathematical structure that would explain why the constants take the values they do. Instead of leaving them as numbers we simply measure and accept. Right now, our best theories treat these values as inputs. We plug them in by hand, based on what we observe, the way you might tune a radio until the static clears. A deeper theory would not need tuning. The right numbers would fall out of the math on their own, the way the ratio of a circle's edge to its width falls out of geometry itself. There is real beauty in this idea. Think of how few rules it takes to describe a snowflake, an orbit, a spiral of stars turning slowly in the dark. Kepler found that planets sweep out equal areas in equal times, a single elegant rule hiding inside the messy paths of wandering lights in the sky. Newton found gravity's pull weakening with the square of distance, a clean pattern behind falling apples and turning moons. Each time, physics has looked closely at something that seemed arbitrary. A simpler rule was often waiting underneath. The dream is that fine-tuning is the same kind of illusion, a puzzle that looks complicated only because we have not yet found the right angle to view it from. One serious attempt at this deeper theory is string theory, which imagines that the smallest building blocks of nature are not points, but tiny vibrating strands of energy. Different vibrations in this picture produce different particles and different forces, the way different notes come from the same guitar string, held at different lengths. It is an elegant image, but string theory does not point to one single set of constants. Instead, its mathematics allows for an enormous number of possible universes, each with its own version of the constants, sometimes called the string landscape. Rather than explaining why our numbers are special, it suggests there may be an almost unimaginable range of numbers that were always possible. This creates a strange kind of tension. Unified theory was supposed to narrow things down, to show that our universe's numbers were the only ones the math allowed. Instead, some versions of string theory widen the possibilities instead of shrinking them. The mystery does not disappear, it simply changes shape, moving from why these numbers to why this particular universe out of so many that seem mathematically allowed. Other researchers hold on to a quieter hope that some future equation, perhaps simpler than anything we have now, will show that only one consistent set of constants was ever possible. In that version of events, gravity's weakness, the strong force's grip, the electron's mass would all be locked together, unable to vary independently, the way the three angles of a triangle cannot vary without changing each other. If that turns out to be true, fine-tuning would stop looking like a coincidence and start looking like an inevitability, a shape that simply had to be this way. No one currently has that equation. What we have are pieces, elegant in their own right, but not yet joined into the single quiet sentence some physicists imagine is waiting to be written. It is worth sitting with how strange this search is. We are looking for a kind of beauty we have not seen yet, using clues from a kind of beauty we have already found in orbits and waves. And the gentle curve of space-time itself, maybe that deeper theory exists and is simply beyond the reach of any mind built from atoms inside the universe, it explains. Maybe it does not exist at all, and the constants really are just numbers, brute facts with no reason behind them, the way a coin might land on heads without any deeper story about why. Both possibilities stay open tonight, resting quietly beside each other in the dark. Neither one confirmed, neither one dismissed. The equations we already have are beautiful enough to keep searching by, even without knowing yet what they are searching for. Picture a scale so finely balanced that a feather could tip it. Now imagine that scale has held steady for 13 billion years. This is the strange calm at the center of tonight's wandering. The constants we've been describing are not just precisely tuned, they also appear to be remarkably stable, holding their values across almost the entire history of the universe. But how do we know they are stable at all? And what would it mean if somewhere in the vast dark they were not? The fine structure constant is a good place to rest our attention here. It is a small number, roughly 1/137, that describes how strongly light interacts with charged particles like electrons. It shapes the color of starlight, the structure of atoms, the very possibility of chemistry. If this number drifted even slightly over billions of years, the physics of the early universe would look different from the physics of today. Starlight from ancient galaxies would carry a subtle fingerprint of that difference, a shift in the exact wavelengths where atoms absorb and emit light. Astronomers have gone looking for that fingerprint. They study light from distant quasars, brilliant beacons powered by matter falling into supermassive black holes. Light that left its source billions of years before Earth existed. By examining how that ancient light was absorbed by gas clouds along its path, researchers can check whether the fine structure constant back then matches its value now. Most studies find no significant difference. or one too small to be certain of. A few have reported hints of tiny variation, though these results remain contested and have not been confirmed by independent teams using different instruments. This is where the question grows delicate. If the constants have held steady since nearly the beginning, that steadiness itself becomes part of the mystery. A universe with constants that drift wildly would likely be unstable, unable to hold stars together long enough for anything complex to form. But why should the constants be so exactly fixed, rather than merely close enough? Some researchers wonder if there is a deep symmetry in nature that locks these values in place, a hidden structure that forbids drifting, the way a law of conservation forbids energy from simply vanishing. Others take a different view. Certain theories that try to unify gravity with the other forces, including some versions of string theory, actually predict that constants like this, one, might change very slowly over cosmic time, tied to the slow evolution of extra dimensions, curled up too small for us to see. If such drift exists, it would likely be too gentle to notice across a human lifetime, or even across the lifetime of a civilization. It would only reveal itself across spans of billions of years, the kind of timescale that makes a single human life feel like the blink of a single eye. There is also the strong nuclear force to consider again here, the force that binds protons and neutrons together inside the nucleus. If it had been slightly weaker across cosmic history, stars might have struggled to fuse hydrogen into helium, and the long, patient burn that lights up the night sky might have flickered out early. If it had been slightly stronger, stars might have burned through their fuel too fast, collapsing before life had any real chance to emerge nearby. The fact that this force appears steady, not just precisely set, but precisely held, adds another layer to the puzzle rather than resolving it. Think of it like a tightrope walker who has been crossing the same wire for 13 billion years without a single wobble. We can measure the wire's tension today. We can look far down the wire into the past using the light of ancient quasars. And so far, the wire looks the same the whole way across. That could mean the wire is simply built that way, unchangeable by its very nature. Or it could mean we have not looked closely enough or far enough to catch it swaying. Neither explanation is fully satisfying, and neither is fully ruled out. A universe with drifting constants seems harder to imagine surviving long enough to notice its own drift. A universe with perfectly fixed constants raises the question of what fixed them and why those particular values. Both paths lead back to the same unfinished question we have been circling all along, the question of whether the numbers governing existence were chosen, selected, or simply happened to be the ones we are here to measure. For now, the quasars keep sending their ode light across the dark, carrying whatever answer they hold, still too faint and too far for us to read with certainty. The wire holds steady, as far as we can tell. Whether it always has, and always will, remains one more question, resting quietly in the dark, waiting for a patient mind to look again. Somewhere beyond the edge of what we can see, there may be other universes. We cannot visit them, we cannot photograph them, we cannot even be sure they exist. And yet some of the most careful thinkers in physics believe they might be the best explanation we have for why our own universe seems so strangely well suited for existence. The idea goes by a familiar name now, the multiverse. Picture it not as a single sky above us, but as an endless field of bubbles, each one a separate universe, each one forming with its own set of constants. In one bubble, gravity might be far stronger than it is here. In another, the strong nuclear force might be too weak to hold a nucleus together at all. Most of these bubbles, if they exist, would likely be empty, Silent, no stars, no atoms heavier than hydrogen, no chance for anything like a listener drifting towards sleep tonight. Our universe in this picture is simply the one where the numbers happen to line up, not because it was chosen, not because it was designed, just because, among endless tries, some bubble had to land on constants that allowed stars to burn and carbon to form and water to stay liquid long enough for something curious to arise and start asking questions. It is a strange kind of comfort, in a way. It removes the sense that we are impossibly lucky and replaces it with something closer to inevitability. If enough universes exist, then a life-friendly one becomes not a miracle, but a certainty, however rare. But here the trouble begins, and it is worth sitting with honestly. We have no way to observe another universe, not with any telescope we have built, or any we can imagine building. If these other universes are truly separate, forever beyond our light and our instruments, then the multiverse is not something we can test in the way we test other ideas in physics. We cannot run an experiment. We cannot gather new data from a bubble we will never reach. Some physicists find this deeply troubling. A theory that cannot be checked, they argue, sits at the edge of what counts as science at all. It offers no prediction we could someday confirm or rule out. It explains everything after the fact, which is exactly the kind of explanation good science tries to avoid. Others push back gently. They point out that certain versions of multiverse thinking do come bundled with testable ideas, even if the bubbles themselves stay hidden. Inflation, the theory describing the universe's earliest and fastest expansion, naturally produces many separate regions once you follow its equations to their logical end. If inflation is real, some argue, a multiverse may simply be a consequence we cannot avoid, whether or not we ever confirm it directly. There is also the question of how the constants would even get set differently from one bubble to the next. String theory, one leading candidate for a deeper description of reality, suggests there could be an enormous number of possible ground states, each with different physical constants. Some estimates run past 10 to the 500th power, whether all of these possibilities are actually realized somewhere, or whether only one of them describes anything real, remains completely open. It helps to remember that the multiverse is not one single tidy idea. There are several competing versions, built from different starting points in physics, and they do not always agree with one another. Some picture bubbles separated by ordinary space. Others picture entirely separate mathematical structures, with no shared space or time at all. Scientists have not settled on which version, if any, resembles what is actually out there. And so we are left in a quiet, honest place. The multiverse offers one way to make peace with a universe that looks fine-tuned for existence. It says, in effect, that fine-tuning is what you would expect to find once in a great while among countless failed attempts. But it asks us to accept the existence of things we may never see, never measure, and never fully confirm. Whether that counts as an answer, or simply a beautifully shaped question wearing the coat of an answer, is something even careful physicists still debate tonight, in offices lit by desk lamps, chalkboards, covered in equations that may describe worlds none of us will ever visit. Somewhere ahead of us, far past the reach of any calendar, the equations we have written down will still be sitting quietly on their pages. They will not change. The strength of the strong force, the mass of the electron, the strange near-zero value of the cosmological constant. These numbers seem fixed, at least as far as we can tell, but the universe around those numbers will keep moving slowly, the way a glacier moves, indifferent to whether anyone is watching. Picture the sun, a few billion years from now, swelling into a red giant. Its outer layers will stretch outward, quiet and enormous, swallowing the inner planets in a soft, gradual way rather than any sudden violence. The physics that makes this possible was set at the very beginning. The same balance of gravity and nuclear force that let stars ignite in the first place will eventually let them die. It is the same knife edge we have circled through this whole episode, just viewed from a later chapter. Farther out, whole galaxies will drift together. Andromeda and our own Milky Way are already approaching each other, pulled slowly across the dark by gravity, that faint and stubborn force we still cannot fully explain. When they merge, new stars may form from the compressed gas of the collision, sparked to life by the same delicate rules of fusion that let stars burn now. Nothing about the constants will need to change for that to happen. They were tuned, if that is even the right word, once, and apparently for good. And yet time itself seems to be working against structure. Dark energy, the mysterious pressure pushing space apart, appears to be accelerating that expansion. If this continues, distant galaxies will eventually vanish from view, not because they moved away in any ordinary sense, but because the space between us and them will stretch faster than light can cross it. Some researchers picture a future where the sky empties out, one galaxy at a time, until only our own gravitationally bound neighborhood remains visible. Whether that is truly what lies ahead is still an open question. The value of the cosmological constant, so strangely close to zero, remains one of the least understood numbers in physics. It is worth sitting with how strange this is. The same fine-tuning that lets atoms bond, that lets carbon form inside stars, that lets water stay liquid on a rocky world, will keep operating for as long as those constants hold. But we do not actually know if they will hold forever. Some physicists have wondered, gently and without much evidence either way, whether constants might drift by unimaginably small amounts over cosmic time. If they did drift, even slightly, the balance that allows stars to burn or atoms to stay together might shift too. So far, careful observations of distant light have found no clear sign of such drift. The idea remains speculative, a question left open rather than answered. Even if the constants never change, the universe will. Stars will exhaust their fuel. New stars will form from the gas those older stars scattered into space when they died. Elements heavier than hydrogen and helium, forged inside dying stars, will keep seeding new solar systems with the raw material for planets and perhaps for chemistry complex enough to be called life. In this sense, the fine-tuning we have been describing is not a single event from the distant past. It is closer to an ongoing hum, still shaping matter in the deep future in ways almost identical to how it shapes the sky above us tonight. There is a quiet, almost eerie comfort in that thought. The equations we cannot fully explain, the reasons the constants sit exactly where they sit, will not resolve themselves as the universe grows older. They will simply keep operating silently, the same way they have from the very first fraction of a second. Whether some deeper theory eventually explains why the numbers are what they are, or whether they are simply, permanently, without further reason, brute facts of nature, is something today's physics has not settled. Maybe someday, in a future far beyond our own, some form of intelligence will look back on this same puzzle with better tools than ours. Maybe they will find the answer we could not, or maybe the answer does not exist in any form we would recognize, and the fine-tuning will remain, forever, a beautiful and unexplained feature of the only universe we have ever known. For now, the equations sit in silence, patient, unresolved, doing their quiet work in the dark. If the constants really are tuned with such care, a quiet question follows close behind. What does that tuning mean for life beyond our own small planet? If the universe had to thread a narrow needle just to allow atoms, stars, and chemistry, does that needle open a door for other worlds too? Or does it make our own existence even more lonely and rare? Picture the calcium resting in your bones right now, as you lie still and listen. It was forged inside a star, in the final violent moments before that star scattered itself across space. The iron in your blood came from a similar furnace. The same is true for every living thing we know of, every leaf, every cell, every breath. If the constants of physics are truly tuned to allow carbon, oxygen, and the long chemistry of life, then that tuning did not just make us possible. It made us out of star material, using the very same forces that shaped galaxies. This is where the fine-tuning question quietly turns outward. If our universe's constants allow stars to burn slowly, forge heavy elements, and scatter them into space, then in principle, that same tuning could be doing this everywhere. Wherever there is a star like our Sun, going through the same slow nuclear steps, similar elements should appear. Wherever there is a rocky planet, at the right distance from its star, warmed just enough for liquid water, similar chemistry might unfold. The very fine-tuning that puzzles us may also be the reason the universe seems so generously suited to making life again and again, in many places, not just once. But here the open questions multiply rather than settle. One view holds that if the constants are tuned for stars and chemistry in general, then life may be a natural consequence almost anywhere the right conditions gather, quiet and ordinary rather than rare. Under this view, our existence tells us little about how common life is. The universe's laws simply permit it, the way gravity permits rain to fall, wherever the ingredients are present. A competing view takes the opposite path. Some researchers wonder if the tuning is so exact, so narrow, across so many separate constants at once, that even a universe capable of forming stars and carbon might still fail to produce life through some other missing piece we have not yet identified. Perhaps the physical constants only clear the first hurdle. Perhaps something else, still unknown, decides whether chemistry ever becomes biology. Under this second view, our presence here might be closer to a singular event than a common outcome. Even within a universe built for it, we simply do not have enough examples to know which view fits reality. We have observed only one planet where life took hold, and we cannot yet see clearly enough into other solar systems to know how often the necessary chemistry gathers itself into something living. The fine-tuning of the constants may set the stage everywhere, and yet the play itself might only be performed here, or it might be performed on countless worlds we have not yet found a way to see. There's a strange comfort in this uncertainty, rather than a discomfort. It means the universe still holds room for wonder on the grandest scale, not just about how existence began, but about how far its consequences reach. If the constants are tuned the way they appear to be, then somewhere in that tuning may be an answer to whether we are rare or common, whether the universe is quiet or filled in ways we simply cannot yet detect from here. For now, what we can hold on to is this: the atoms in your body followed the same rules that shaped the first stars, the same rules that hold planets in their orbits, the same rules that may or may not have been tuned by something we do not understand. Whether that tuning is a sign of many hidden universes, a deep bias built into our own observation, or something else entirely, it connects you to the widest scale of the cosmos in a very direct and physical way. You are not separate from these questions. You are made from their answer, whatever that answer turns out to be. As you drift towards sleep tonight, You can let that connection settle in gently, somewhere above you. Other stars may be finishing their own slow work, scattering their own elements into the dark, perhaps building the ingredients for other quiet worlds we will never know about. The same careful balance of forces that allowed you to exist may be repeating itself endlessly or only once across a universe that still keeps this particular answer to itself. We have come a long way tonight, through nuclear forces and carbon resonances, through the strange near-zero hum of the cosmological constant, through the quiet arithmetic that lets a star burn slow enough for someone to watch it. We have touched theories that reach for a multiverse, and theories that ask if this whole search for meaning is just a trick of being here to ask the question at all. None of it was settled. All of it was real. Somewhere out past the edge of what any telescope can reach, there may be other universes, with other numbers written into their forces, or there may be only this one, alone. Its constants simply what they are, for reasons we have not yet found. Both ideas remain open. Both are held gently by scientists who keep working, and by the rest of us who simply keep wondering. That is allowed. Wonder does not need an answer to be worth carrying with you into sleep. Picture, for a moment, a small blue planet turning slowly in the dark. Its ocean lies flat and silver under a rising moon, barely moving, holding the sky's reflection like a hand holding water. On this planet, atoms that only barely hold together are holding together anyway. A nuclear force tuned to a hair's width of difference is letting carbon form in the hearts of old stars, letting that carbon drift across the dark for billions of years, letting it become the calcium in a bone, the salt in that quiet ocean, the quiet rhythm of a chest rising and falling under a blanket. All of that improbability resting now, doing nothing more dramatic than letting someone fall asleep. Above that ocean, the galaxy turns too, so slowly that a human life is far too short to see it move at all. Its spiral arms hold light from stars that finished burning long before any of us were born. Some of those stars had planets. Some of those planets may have had oceans of their own, and skies, and maybe something that noticed the sky and wondered about it, the way you are wondering right now. We do not know. We may never know. The not knowing is not a failure. It is simply the size of the question, sitting quietly in the room with us. The forces that shaped all of this, gravity pulling gently, the strong force binding tightly, the strange steady push of dark energy loosening space itself, do not explain themselves to us. They simply act the same way they have acted since the universe was a fraction of a second old. The same way they will act long after tonight is over, whether they were tuned by chance, by some deeper law we have not found, by a vast unseen collection of other universes, or by something we do not yet have words for, is still an open question resting in the dark alongside all the others. There is a kind of peace in that. You do not need to solve the universe before you can rest inside it. The scientists asking these questions will still be asking them tomorrow, patiently, carefully, the same way the stars will still be burning, and the moon will still be pulling gently at that quiet ocean. Nothing tonight requires you to finish it. The mystery will keep. It has kept for billions of years already, so let the picture stay soft. The planet turning, the ocean resting, the galaxy circling slowly overhead, indifferent and beautiful, made of the same improbable numbers that somehow allow warmth and breath and rest. You are a small, safe part of something enormous and unexplained, held not by an answer, but by the simple fact that for reasons no one has fully worked out, a universe like this, one was able to make a night like this one, and a listener like you And this exact quiet moment before sleep, we may understand more of it someday. We may not. Either way, the universe does not ask you to solve it before you close your eyes. It only asks you to notice it once in a while, the way you are noticing it now. Let the numbers stay mysterious. Let the stars keep their secrets a little longer. Let your body grow heavy and still, the way the universe itself seems to prefer things eventually settling, slowing, resting. Good night. Out there in the dark and improbable world, subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.